Welcome back, everybody, to the end of the week. It is the end of week 14. We're on April 24th, 2020. I'm going to begin, as is usually the case, with announcements, review, and introduction to regression. So this is pretty straightforward. So keep going now with the announcements. First announcement, as you know, today is the day to turn in homework number 5, which is your final homework assignment for the semester. The way that I'm going to proceed from here is that I'm going to start to begin to offer extra credit. I have been trying hard to get SPSS up, but if I'm having trouble getting it up onto my system, then I suspect you might be too if you've tried it. Therefore, I might have to go exclusively with Excel this year, which would be a little different, but then again, this whole year has been a little different. So that might be the way I'm going to do things. Well, the way I'm thinking about it is this, is I'll put out a number of extra credit assignments, and if you complete all of them, then it would be a total of 10 points. And if it's 10 points, then that makes up for any missed or, first of all, missed homework assignments. So let's say you didn't do one altogether, forgot about a date, whatever happened, that would take the place of an entire homework assignment. Otherwise, you would have some points to spend on gaps in your homework assignment. So if you got 8 out of 10 and you were hoping to get a 10, and you ended up doing a extra credit assignment that was worth 2 points, well then, now you ended up getting 10 out of 10. So that's how it's going to work in terms of extra credit. So once you complete the extra credit, I go directly into your homework assignment and put in missing points. That's basically how I've been doing it for years, and I think that's been probably the fairest, because that's homework assignments are 30% of your grades. So people don't seem to have trouble with accepting that it's 30% weighted points. Okay. The only other thing to tell you about, I think today, besides the homework assignment being due and also the extra credit, is that we have the exam next Wednesday. It's the 29th. It's going to cover almost exclusively t-tests and correlations. By now, you're very familiar with both. I have been constantly feeding you questions in the form of reviews, getting you really familiar with the difference between accepting and rejecting a null hypothesis, whether it's from a calculated and critical standpoint or from a p-value standpoint. You know that the differences between the t-test and correlation include things like how the null hypothesis is phrased. I mean, I can go on. I've given you so many I think opportunities and little tasks to do around this. So I'm feeling pretty good about, at least on my end, how much I've offered. Now, if you need more help, that's fine too. But you'll have to let me know. That's the one thing, is I'm a really bad mind reader. I'm just no good at reading people's minds. So you're going to have to help me with that. We'll do the review here in a moment. You might ask me, was there anything on regression going to show up on the exam number 3? And I'll tell you one thing. If anything on regression shows up on exam number 3, it's just going to be basic terminology. It's not going to be an equation by any means. That would be, in my opinion, really unfair. So that's not what I'm going to do. I'm not going to give you an equation to figure out that pertains to regression at all. That's, again, as you'll see the equations for regression and say, okay, well, that's probably a good idea. I think you have enough to do with t-test and correlations. That the point here isn't to overwhelm. The point here is to make you competent. So that's kind of where I'm aiming. So without that, I think what we'll do is we'll continue on with the review portion. So now we'll move on to review. And I understand that the picture that I have up for you today is called Little Louie. I don't know where they came up with these names, but apparently the name of this cat is Little Louie. So I say hello to Little Louie, everybody. And go ahead and we'll get ready for our review. So probably a good idea to have out a piece of scratch paper or something you can just write on for a few minutes. Okay, all right. We'll go ahead and begin with review. Okay, everybody, so we are back with our review now. And I've got some, I think, good questions for you, and hopefully they'll help you. If they are any that you struggle with, it's just a good indication that it's just an area that deserves a little more attention. So let's go ahead and go through these now. So we'll go ahead and do number one, true or false. T-tests are tests of significant differences between the averages of two groups. Again, true or false. T-tests are tests of significant differences between the averages of two groups. Okay. Number two, true or false? Correlations indicate causation between variables. True or false? Correlations indicate causation between variables. I think I put too many E's there. There we go. Let's take a look at number three. True or false? Two sample independent t-tests compare the averages of samples from two distinct and unrelated populations. Let's try it one more time. True or false? Two sample independent t-tests compare the averages of samples from two distinct and unrelated populations. Number four, true or false? A two-sample dependent t-test compares the mean of a sample and the mu of the population from which it was taken. True or false? A two-sample dependent t-test compares the mean of a sample and the mu of the population from which it was taken. Okay, number five. Correlations are bivariate statistical analyses. Number five, true or false? Correlations are bivariate statistical analyses. Okay, number six, true or false? When a p-value is greater than 0.05, the null hypothesis should be rejected. Let's do that again. True or false? When a p-value is greater than 0.005, okay, the null hypothesis should be rejected. Okay, we're on number seven now. True or false? When a calculated t-value is negative, we should assume a negative relationship among the variables. True or false? When a calculated t-value is negative, we should assume a negative relationship among the variables. Number eight, true or false? The test for degrees of freedom for correlations is n-2. I'll try it again, true or false? The test for degrees of freedom for correlations is n-2. Number nine, true or false? When the y value on a scatter plot rises, as the x value rises, we have a positive correlation. Try it again. True or false? When the y value on a scatter plot rises, as the x value rises, we have a positive correlation. Okay. And finally, number 10, true or false? Correlation coefficients can be greater than plus or minus 1. True or false? Correlation coefficients can be greater than plus or minus 1. Okay. Hopefully you were able to record all the answers for these as I was going through them. I tried to go at a pace that was relatively easy for you to kind of follow and keep up with. So the next thing we're going to look at, if you've had a chance to kind of process these, is the responses. So go ahead and be ready for those. Okay, so now I'm back with the answers. I'm sorry I had to kind of cover up our cat friend, but I'm sure he'll be back at some point. So let's go ahead and I tried to line these up so that they're fairly parallel with each other so it's easier for you to see. So question number one, true or false? T-tests are tests of significant differences between the averages of two groups. And I said number one, true. This is a fairly comprehensive definition of t-tests. In other words, the two groups could be the samples of two independent populations or two distinct and unrelated populations. The two groups could be samples from the same population, or the two groups could be one sample and the population from which it was taken. So again, all three t-tests we've studied in this class can be considered true under this definition. So I tried to make that as plain as possible. Okay, moving on to number 2. True or false? Correlations indicate causation between variables. Here's was my very non-dramatic answer. False. You will fail out of college and life if you believe this. So, yeah, enough said, right? Okay. So let's take a look at number 3. I'm going to get these things evened up for you. Okay, number 3, true or false? 2 sample independent t-tests compare the averages of samples from 2 distinct and unrelated populations. And the answer for number 3, true. The key term here is samples from 2 distinct and unrelated populations. That's really, if you're thinking about a visual, that's how it should really look. I drew pictures for you from, I think it was last week I really got into the picture drawing business for a minute. You can remember how I drew the 2 populations with the samples from them. Yeah, that's independent t-test. Okay, number 4. I think that's squeezed onto the screen. Maybe not. We need to go down a little bit further. There we go. Okay. True or false? Number 4. A 2-sample dependent t-test compares the mean of a sample and the mu of the population from which it was taken. Nope. No, I'm sorry. That's false. This is a description of the 1-sample t-test. This would have been a correct answer if instead of a 2-sample dependent t-test, I had simply stated a 1-sample t-test. But that's not what I said, so can't be true. Okay, take a look at number 5. Okay, I'm just trying to be precision here. There we go. Okay, true or false? Correlations are bivariate statistical analyses. Number 5, I said true. Don't be fooled by big words. Bi means 2, and there are only 2 variables on a scatter plot, the x and the y. Okay, it should be pretty straightforward. Number 6. Okay, next up. Okay, true or false? When a p-value is greater than 0.05, the null hypothesis should be rejected. No, it's the opposite that's true. So this is false. It is the opposite. When the p-value is greater than 0.05, the null hypothesis should be accepted. So that's probably good review. Number 7, pull up the answer here. Okay. True or false? When a calculated t-value is negative, we should assume a negative relationship among the variables. False. This conflates t-tests and correlations. I mixed them up, okay, on purpose so we could be clear about what they really are. In reality, we use the absolute values for t-tests, so the negative does not indicate a negative relationship between the variables. In fact, the negative doesn't even matter that much when we're talking about calculated t-values, okay? That's something we should really make sure gets dialed in before the exam, because that's something that students can easily mix up, and frankly, that's not what I want to happen. Number 8, true or false? The test for degrees of freedom for correlations is n-2. And number 8, yep, the answer is true. The test for degrees of freedom for correlation is indeed n-2. Number 9, let's take a look at this. Okay. When the y value on a scatter plot rises, as the x value rises, we have a positive correlation. I said 9, true. When the y value on a scatter plot rises, as the x value rises, we do have a positive correlation. If you need a visual of this, I'm happy to supply one for you. Let me just pull this over just for a second. Okay, here it is. Okay, I'm going to use black ink first. Okay, let's go ahead and think about this. Okay, you've got a scatter plot. Okay, you have an x value. You have, oops, it should be an x. There you go. You have a y value. Okay. All right. If you think about this visually, okay, it's asking is it true that when the x is rising, so the x rising, okay, if this is, usually this is the lower value, this is the higher value. So if it's going this direction, it's increasing, okay? Increase. Well, yeah, I'll help you out here. I can spell this, I am a champ. Okay, increase. Okay, so you already know that if there's a value, x is increasing. Okay, think about this. If y is also increasing, okay, again, I won't spell it out this time. It's going this direction because this, of course, would be 0, 2. So it's indicating that as this value is getting larger, this value is getting larger too. So it would be going in this direction, which, as we already know, is a positive. Now, if you think about the opposite of that, it would read something like, as x is increasing, y is decreasing. If that had been the case, let's go ahead and just change the color. If we had said, as x increases, y is decreasing, clearly we wouldn't see a positive. We would see a negative. Okay. Okay, I'll just switch this back for you. There you go. Okay, so you got a visual there. Hope that helped you a little bit. Okay, so now you can see why that number 9 is true. And finally, number 10. True or false, correlation coefficients can be greater than plus or minus 1. False, correlation coefficients cannot be greater. I was confused. I saw in a couple of homework assignments that I've been checking preliminarily, okay, a calculated value for, I think a student ended up being, over 1. Okay, I'm just going to make the number up. I had to write back and say, no, actually it can't be, because the range at which a correlation coefficient can be found is only between, remember how we saw that graph where here's -1, that's like the end, that's where you're going this direction and it's a straight line, okay? And, oops, one second here, gee whiz, didn't even mean to do that. Okay, by contrast, if we're talking about the other end, okay, by definition, a positive value of a 1.00 is a straight line. You can't get any more. You can't get any more straighter than the straight line. And in the middle of both is a 0. So when we get closer out to either -1 or when we get closer to +1, we get stronger. Okay. When we get into the middle, it's weak or no correlation. But that's the thing. These are the outer limits of correlation coefficients. You can go to a -1 or you can go to a +1, and those are going to be straight lines, but you can't go beyond them. Just by definition, you can't. So hopefully my diagram here helped you out a little bit. Okay. Okay, everybody, so I decided to give you a bonus round today, and the reason why is because I have the presentation queued up for the regression, but it's not horribly long, and I figured it might be more helpful to go over just a couple more questions that I tend to give, at least in terms of form, on exams like exam number 3. So again, this is just a little more practice, and it's not going to take very much time. Okay, so this is actually, I just entitled it review number 2. Okay, look at this question. It's multiple choice this time. The first group were true and false. This is going to be multiple choice. Excuse me, number 1, a social worker wants to compare the average rate of incomes below the poverty line in Sacramento and the average rate in California. So there's going to be a comparison between poverty rates in Sacramento, and that would be Sacramento County alone, and the average in California. Okay, this particular social worker should use A, a 1-sample t-test, B, a 2-sample independent samples t-test. I guess that's redundant, so we'll just say a 2-sample independent t-test. Okay, again, redundant here. Okay, C, a 2-sample dependent t-test, and D, a correlation. So those are going to be our choices for number 1. Let's take a look at number 2. A calculated correlation coefficient is found to be negative 0.75. The critical value is 0.63. We should A, accept the null hypothesis, B, reject the null hypothesis, C, change the null hypothesis, and D, ignore the null hypothesis. Okay, think about that. Now number 3, okay, give you some space, social distancing between these questions. Okay, number 3, a calculated t-value is negative 4.32, while the critical t-value is 2.60. We should, again, A, accept the null hypothesis, B, reject the null hypothesis, C, change the null hypothesis, or D, ignore the null hypothesis. Number 4, calculated correlation coefficient is 0.56, while the critical value is 0.78. The p-value will it be less than 0.05, exactly 0.05, C greater than 0.05, or D less than 0.01? Finally, number 5, a comparison of average GPAs between BSW and MSW students gives a p-value of 0.03. This indicates that, okay, be careful here, A, no statistical significance was found, B, there is no difference between the averages, C, the critical t-value must be greater than the calculated t-value, or statistical significance was found. Okay, glance at that fact pattern, give it some thorough thought, okay, and then we'll return with these answers. And now the answers. For review round 2, we're going to start with number 1. Social worker wants to compare the average rate of incomes below the poverty line in Sacramento County and the average rate in California. She should use, correct answer is A, a one-sample t-test. I said that one-sample t-test is the correct response as the means of a sample is being compared to the larger population from which it was drawn. And in this scenario, that's exactly what happened. Sacramento County is in California, so obviously it's a sample from the larger population, and we're comparing the average in Sacramento County to the mu, which in this case would be that of California, which is the greater population. Okay, so that was the only one that made any sense out of those choices. Hope you got it right. Let's take a look at the question number 2. Okay, I'll give us some space. Seems to be the theme nowadays. Okay, we're going to pull up number 2. Okay, a calculated correlation coefficient is found to be negative 0.75. The critical value is 0.63. We should A, accept the null hypothesis, B, reject the null hypothesis, C, change it, and D, ignore the null hypothesis. As you can see on the right-hand side, the correct answer is letter B. Okay, reject the null hypothesis since the strength, and the strength is just this number right there, okay, 0.75, okay, the strength of the calculated correlation coefficient is greater than the strength of the critical. The fact that it's negative only tells us the direction of the correlation. That's all. So it's not a matter of whether or not it was positive or negative when it comes to judging whether or not to accept or reject the null hypothesis. We're going by the strength, not the direction. So B is the correct answer. Okay. Go to number 3 now. And we'll go to number 3 over here. And we'll send you 2 back down. It's not your time yet. Okay, number 3. A calculated t-value is negative 4.32, while the critical t-value is 2.60. We should, same answer choices as before, accept the null, reject the null, change the null, or ignore it. I wouldn't recommend ignoring it. Okay, number 3, the correct answer again is B, reject the null hypothesis because the absolute value, see this? The absolute value, okay? The absolute value of the calculated t-value is greater than the critical t-value. So the absolute value of negative 4.32 is 4.32, and that is greater than 2.60. So again, B would be the correct answer. Now it's 4's turn. Okay. There we go. 4 was excited to be here. Okay, number 4, a calculated correlation coefficient is 0.56, while a critical value is 0.78. The p-value will thus be what? A, less than 0.05, B, exactly 0.05, C, greater than 0.05, or D, less than 0.05. Well, here's your answer right here. It's letter C. Because the critical value is greater than the calculated value, we would accept the null hypothesis. Okay? This also means that the p-value would necessarily be greater than 0.05, because that's the only time it's greater than 0.05 is when we've accepted the null hypothesis. Okay? All right, so that is the answer to that one. We need to go over it again. That's the beauty of this whole taped lecture thing. You can you can rewind in your own way. Okay, take a look at number 5. All right, number 5 coming right up. Okay, let's go ahead and see if I can. I'm just going to go ahead and read this for you. Comparison of the average GPAs between BSW and MSW students gives a p-value of 0.03. This indicates that A, no statistical significance was found, B, there is no difference between the averages, which is effectively the null hypothesis, okay, and C, the critical value, the critical t-value must be greater than the calculated t-value. Well, none of these 3 choices can be true because look at the p-value, okay? Is that over or under 0.05? It's under. So we would have A, rejected the null hypothesis, okay, and B, found statistical significance, because that's really what the question is. So the only answer, and I indicate this over here as well on number 5, okay, D, because the p-value is 0.03, we know that the null hypothesis shall be rejected, thus only D is the correct response among the choices, okay? All right, well, hopefully you did well on those 2. I felt like it was worth our time to just kind of go through that a little bit because, again, I know people get ramped up around exams, and this should hopefully take some anxiety away and help you kind of understand what questions are going to likely be, you'll be seeing, or at least the form and kind of the way to kind of think about the questions, how you attack them. So that's why I did that. Okay, now we'll move on to regression. Okay, everybody, now we're at the PowerPoint that I use to introduce to students the simple linear regression, which is also the title of Chapter 12. If you refer to this as simple linear regression, I'll know what you're talking about. That's more of the formal long term, but if you just simply said regression, I know what you're talking about, and so do you, and that's probably the most important thing. So we'll go ahead and go through some of this. I wouldn't get too wrapped around the axle about the terminology because I'll be hitting it hard next week too, but this is just kind of a way to introduce you to it. So let's go ahead and take a look at what we mean by simple linear regression. Okay, I'm going to give an overview. First thing you need to know is the simple linear regression is a bivariate or 2-variable statistical application, which again, pretty much was the same with chi-square and correlations as well. Okay, t-tests, yes. So that's pretty much what we've covered in class, but our book stresses that, so I thought I would do that too. It's called simple, since what we're doing is trying to isolate one variable used to predict or infer the value of another. We'll know a little bit more about that in a second, but we have the X and the Y when we're talking about correlations, and that's the one thing you absolutely need to know about regression. Regressions apply to correlations. That's why I teach regressions directly after correlations, even though the book has it a little bit differently. Pearson's oh, here we go. Am I good or what? Here we go. Pearson's R correlation is used as a basis for these inferences that we're talking about here. So again, you're really not going to be doing much of a regression without a correlation. You need to have a correlation to do a regression. So that's the first thing. So just as in the past we said, a scatter plot is what you'd use for a correlation. A contingency is what you use, or a contingency table, or a cross tabulation is what you use for a chi-square. You're not going to be doing a regression on anything other than a correlation. Okay. we are using the correlation line to locate values. So this is where we're trying to isolate values on a correlation to see if we can predict what the values will be. So again, this is like kind of like magic trick without actually being a magician. Actually, there's no magic at all. It's all math. So sorry about that if you were getting excited about magic. Anyway, we'll keep going. Meaning of a linear regression. The first thing you need to know is literally regression means going back or referring. So we're referring to specific x's and y's on a correlation in order to find the values. This is what makes a lot of statistics so valuable to people who are trying to make predictions. You've heard about flattening the curve with obviously the coronavirus. And again, even this reference to curve is pretty much a reference to statistics as well. So again, we're using statistics in a lot of ways to try to make predictions, and that's exactly what a regression does, is tries to make predictions about values. Okay, measures only relationships that are linear between two variables. So if you're looking at a correlation and it's got no correlation, so you have a correlation coefficient of like 0, that's not going to work. We need to have a linear relationship between them. So hence the name simple linear regression. Variables must be at the interval ratio level of measurement y, because that's the requirement for correlations. Researchers manipulate the x variable and find the value of the corresponding y value. Yeah, that's the way I really look at the independent versus dependent variables. It's not independent and dependent because one's causing change in the other. That's blasphemy in this class. You don't say that a correlation causes. The best way to think of an independent variable, it's the one that the scientists kind of mess around with. They have some control of. Whereas the y is what they're actually trying to study and observe. I know I mentioned that in an earlier lesson, but I thought it was good to kind of go back over it again. So looking for an x, we ran into a y. Okay, that harkens back to a song. I don't know if you know that one. Maybe I should pass out Skittles if anyone can figure out what the reference is here. I'll give you a hint. It's the Beastie Boys. Okay, so looking for an x, we ran into a y. Looking for an x, we ran into a y. Okay. That's if you know anything about the earlier Beastie Boys stuff, you probably think that's funny. If you don't, you probably won't find it funny. Anyway, we'll go on to the next slide. Okay, simple linear regression in the context of social sciences. Simple linear regression helps to make informed predictions about behaviors and conditions and interventions. So we can predict, for example, how many times an intervention is going to need to be used to achieve a certain result. And if we know, like for example, in terms of correlation, we know what magic number it is, whether it's 6 hours of this kind of intervention or 12 weeks of this kind. We can predict. We can start to make predictions. So one way is to make informed predictions about behaviors and conditions and interventions. Okay, effects of medications on disorders. We for example, would learn how much medication is required to treat a disorder. Simple linear regressions can help you with that. Okay. Exercise with people in car accidents. Let's say that somebody has lost the ability to use a limb, but it hasn't been, you don't have permanent nerve damage. We can predict on average, or we can predict using correlations about how many sessions somebody's going to need for physical therapy in order to return the control to their muscles. Okay. Causes and effects of medical noncompliance. Absolutely. We can figure out all kinds of things with regard to medical, or I guess you could go the other way on that too, medical compliance. So anyway, these are just examples in the field of social sciences how we can use simple linear regressions. They're also mentioned in books as well, but nonetheless, early intervention for children with speech impediments, absolutely. Depending on how old they are, how many sessions it takes for somebody to get more proficient in being able to speak certain syllables or use certain kinds of vowel sounds. Child maltreatment and chemical dependency. Yeah, I mean, these are all predictive things. These are ways that we would try to help ourselves make decisions based on statistics rather than just kind of going at it and guessing. Again, evidence-based practice is pretty much still the rage. So, this is another way that statistics fits into the bigger picture. Okay, statistical requirements. Some of them you've already heard me mention earlier. Okay, this is one I haven't mentioned. Requires random sampling from a population, which can be difficult. Yeah, it is. It can also be incredibly expensive. You have to take care to make sure that you're not tainting the process by making it non-random. I'm kind of hearkening into your Social Work 111 class right now. You need to make sure that it's a purely random sample from a population. That's one thing that's required for linear regression. Okay. In lieu of random sampling, random assignment to experimental groups. So this is where you have a population of people, and you may have had some say in picking out who they are. But whether you send them to the experimental group or the control group is something you're going to be doing randomly. Again, I feel like I'm leaning into the Social Work 111 template at this point. But again, it's mentioned in the book, so it's definitely something I want to cover here. Okay, values of variables should be normally distributed. So we're looking at a normal curve for each of the values we're looking at. Again, in order to have a linear regression, you're going to have to meet these requirements. Okay, homoscedastic means that there's not too much variance in your variables. I mean, in other words, your variables should be, that sounds weird, that you shouldn't be so much variety in your variables, but it's true that they're fairly stable sets of numbers. They don't wildly vary with like high levels of outliers or something like that. And this is probably the most important. That's why I think I put it in red. You have to have a statistically significant correlation. In other words, you will already have to have a correlation where the calculated value was greater than the critical, or put another way, the p-value is at or less than 0.05. Okay. If you're looking for what the computational equation is for simple linear regression, don't look any further than this slide. Okay. Again, I am not going to put this, I repeat, I almost feel like I need to yell. I am not going to put this in exam number 3 at all. So we're just kind of looking ahead. But since we're looking ahead, does something on this particular slide look familiar to you? It should. Look at this. Look at that right there. Okay, does that look like something we just studied? It looks like the equation for Pearson's R, only it's missing 2 things. It's missing it's missing the square root, and it's missing the y box. So we see we have here the x box, okay, but it's missing the square root sign, and it's missing the y box. Well, that's why I said, does this look familiar? Think back to the equation for Pearson's R. Well, there it is. Okay, this is going to be your simple linear regression equation, and you can see that it's going to be y prime equals a plus bx. Okay, looking for an x, we run into a y. Looking for an x, we run into a y. Okay, but then you've got these other variables, a and b. Well, what's a equal? A equals y bar, and anytime you hear bar, okay, insert your joke here. Okay, no, anytime you hear bar, you're thinking average. Okay, so we have a equals y bar minus b times x bar. And then you say, well, what's b? Well, b is this. So you can see how this equation fits together. Here's the base equation. You can see that the a is this, and you can see that the b is this. So to work your way back up to answer this question, you start here and just kind of go all the way back up. I used to call it skiing up and down the mountain. So anyway, we'll get to that again. This is just to get you familiar with what we're looking at. It's not going to be anything that you're going to have to get too worried about right now. Okay. So with simple linear regression, I gave you an example. Okay. Here are the x values, here are the y values, and you can see going across, just like we did for correlation, okay, we're going to start with x times y and get xy, okay, 3 times 8, 24, 10 times 5, 50, 11 times 3, 33, you get the drill, 5 times 6, 30, come on, we know all this, okay, but then check this out, that look familiar? Should. Same thing we did with correlations. Once we've gone across and gone from the x to the y to the xy, then we just go ahead and square these two columns. So x and x squared, okay, obviously 3 times itself is 9, 10 times itself is 100, 11 times 11 is 121, 5 times 5 is 25, 4 times 4 is 16, and the same here, 8 times 8 is 64, 5 times 5 is 25, 3 times 3 is 9, you get the picture, okay? So again, we're going to keep doing exactly what we did before, except look what we did in addition to what we did in the past with the correlation. Okay, we went ahead and took the average of the x column and the average of the y column. Why? Not why. Why? We're saying why because that's part of the equation that I referred to when I was referring to the a variable. Okay, a couple slides back, but it's okay. We're going to go over this again. Okay, I'm just trying to get your feet wet here. All right. If we're going to chart a simple linear regression, I have an example here. So you can see that this looks to me like if the fact pattern has data points going like this, it's negative. And sure enough, it's negative. In fact, it's a negative 0.88. Okay, see that? Okay, that's pretty straight. The critical was 0.632, so we have a very important element or condition satisfied here. Is this particular calculated value greater than this critical value? You bet, because even though there's that negative there, it's just telling us the direction. The strength is 0.88, okay? That's bigger than 0.632, okay? So now we know. But here's how I did it, okay? From the chart, I took so all of these values you see right here pertain to what we found. I should have had them to this particular side. Should have had them a little closer together, but you can bear with me. See how it says x, sigma x is 79, and then x bar, which would be the average here, is 7.9. Okay, then we see that the sigma y is 56, and we see that because we have 10 values here, the the y bar is going to be 5.6. All right. So you can see all our crazy values here, and they're fine. They're going to be fine when we move the slide along too. Okay, so let's come down here. Okay, all of this, I said we're going to start with B. Okay, look what happened to B. Okay, we knew that there were 10 values. It's the exact same thing we did as before, except we're missing, again, the square root and the y box. But otherwise, it's the same. So once we've run B, we get, at the end, after we've run it all, negative 0.64. And now look at what I did. Remember how I was mentioning the y bar and the x bar from the previous screen? 2 screens. X bar, y bar, okay? Look at that. Y bar, okay, there it is. X bar, there it is, okay? So we just plug this guy there. Yep, multiply, okay? And then we're going to subtract it. It's going to give us that. And then when we plug it all together, effectively what we've created is a new equation. So now for this particular regression, for this particular regression on this correlation, we're going to use this formula. So when we plug in an x, it's going to give us the approximate y value. See, looking for an x, we run into a y. So when we plug in any x value on this, okay, we can find the approximate y value. So just the same as saying this. We plug in an 8 here, okay, so if x equals 8, we put the 8 here, we multiply it times negative 0.64, and then we add it to 11.5. And that's going to give us the approximate y. So for an x of 8, we're going to get an approximate y of 6.38. Okay. For an x of 11, if we plug that 11 in here, okay, we're going to get an approximate y value of 4.46. And if we plug in a 3, okay, we're going to get an approximate y value of 9.58. Let's take a look at this first one real quick. If we plug in an 8, we get an approximate y value of 6.38. Let's go back. Okay. If we plug in an 8, okay, we're going to get an approximate y value, okay, somewhere between these two. Notice that they had 2 right there. That's not really a great example, but if you average these out, you're probably going to find it around the 6. Okay, it's right there. Okay, take a look at the other one, which is probably a little better. If we plug in an 11, we're going to get a 4.46. Let's see. Whoops, wrong way. Okay. See, you can kind of envision if the 11 was here, it's going to be right around here. That's going to be close to 4 since 5 is here. And just to take us all the way through it, because I think we can get a better example here. If we plug in a 3, we're going to get an approximate 9.58. Let's go back. 3, okay. 9.58 is close to 10, so it's going to be around here. Again, it's basically what a regression is doing is thinking about an imaginary line that goes through here, which is called the line of best fit. And that is where all these values are going to be connecting with each other. So when I read you off these values on this screen, it's pertaining to this line of best fit. But before I get too carried away, this was just a primer. I may have gotten a little carried away. Sorry about that. But this is just a primer for you to get to see what this looks like. Now, when we run through more examples on Monday and through next week, okay, you'll get more familiar with this. But again, I always felt like this. If we can end the semester with regression, we did exactly what we needed to do for this semester, because a regression is a skill you at least need to be familiar with. You don't have to be a pro at it. You don't have to be expert. But if you're familiar with what regression is and what it means, and you've seen a couple of examples and maybe tried a couple, this is where you need to kind of conclude your experience with the Social Work 110 class. That's what I firmly believe. So anyway, enough about that. We'll get together at the beginning of next week and keep going with all of this. Don't forget to do your participation quiz for this week. Remember, I'm doing this a little differently. I'm having you do it on the Canvas. Okay, and then we will look more into regression as we go along. Okay? All right. Stay safe. Be well.